Orders of magnitude are written in powers of 10. For example, the order of magnitude of 1500 is 3, since 1500 may be written as 1.5 times 103. Differences in order of magnitude can be measured on their logarithmic scale in decades. Examples of numbers of different magnitudes can be found at orders of magnitude. We say two numbers have the same order of magnitude of a number if the big one divided by the little one is less than 10. For example, 23 and 82 have the same order of magnitude, but 23 and 820 do not. John C. Baez uses orders of magnitude are used to make approximate comparisons. If numbers differ by one order of magnitude, x is about 10 times different in quantity than y. If values differ by two orders of magnitude, they differ by a factor of about 100. Two numbers of the same order of magnitude have roughly the same scale. The larger value is less than 10 times the smaller value. The order of magnitude of a number is, intuitively speaking, the number of powers of 10 contained in the number. More precisely, the order of magnitude of a number can be defined in terms of the common logarithm, usually as the integer part of the logarithm, obtained by truncation. For example, the number 4 million has a logarithm of 6.602, its order of magnitude is 6. When truncating, a number of this order of magnitude is between 106 and 107. In a similar example, with the phrase, he had a 7-figure income, the order of magnitude is the number of figures minus 1. So it is very easily determined without a calculator to be 6. An order of magnitude is an approximate position on a logarithmic scale. An order of magnitude estimate of a variable whose precise value is unknown is an estimate rounded to the nearest power of 10. For example, an order of magnitude estimate for a variable between about 3 billion and 30 billion is 10 billion. To round a number to its nearest order of magnitude, one rounds its logarithm to the nearest integer. Thus 4 million, which has a logarithm of 6.602, has 7 as its nearest order of magnitude, because nearest implies rounding rather than truncation. For a number written in scientific notation, this logarithmic rounding scale requires rounding up to the next power of 10 when the multiplier is greater than the square root of 10. For example, the nearest order of magnitude for 1.7 times 108 is 8, whereas the nearest order of magnitude for 3.7 times 108 is 9. An order of magnitude estimate is sometimes also called a zeroth order approximation. An order of magnitude difference between two values is a factor of 10. For example, the mass of the planet Saturn is 95 times that of Earth, so Saturn is 2 orders of magnitude more massive than Earth. Order of magnitude differences are called decades when measured on a logarithmic scale. Non-decimal orders of magnitude. Other orders of magnitude may be calculated using bases other than 10. The ancient Greeks ranked the nighttime brightness of celestial bodies by 6 levels, in which each level was the 5th root of 100 as bright as the nearest weaker level of brightness, and thus the brightest level being 5 orders of magnitude brighter than the weakest indicates that it is 5 or a factor of 100 times brighter. The different decimal numeral systems of the world use a larger base to better envision the size of the number, and have created names for the powers of this larger base. The table shows what number the order of magnitude aim at for base 10 and for base 1 million. It can be seen that the order of magnitude is included in the number name in this example, because bi means 2 and tri means 3, and the suffix illion tells that the base is 1 million. But the number names billion, trillion themselves are not names of the orders of magnitudes, they are names of magnitudes. That is, the numbers 1 trillion etc. SI units in the table at right are used together with SI prefixes, which were devised with mainly base 1000 magnitudes in mind. The IEC standard prefixes with base 1024 were invented for use in electronic technology. The ancient apparent magnitudes for the brightness of stars uses the base and is reversed. The modernized version has however turned into a logarithmic scale with non-integer values. Extremely large numbers. For extremely large numbers, a generalized order of magnitude can be based on their double logarithm or super logarithm. Rounding these downward to an integer gives categories between very round numbers. Rounding them to the nearest integer and applying the inverse function gives the nearest round number. The double logarithm yields the categories 1.0023 minus 1.023, 1.023 minus 1.26, 1.26 minus 10, 10 minus 1010, 1010 to 10,100, 10100, 10100. The super logarithm yields the categories or negative numbers 0 to 1, 1 to 10, 10 to 1 E10, 1 E10 to 101, E10, 101, E10 to 410, 410 to 510, etc. The midpoints, which determine which round number is nearer, are in the first case 1.076, 2.071, 1453, 4.20 times 10 to the 31, 1.69 times 10 to the 316, and, depending on the interpolation method, in the second case minus 301, 5, 3.162, 1453, 1e 1453. For extremely small numbers, neither method is suitable directly, but the generalized order of magnitude of the reciprocal can be considered. Similar to the logarithmic scale, one can have a double logarithmic scale and super logarithmic scale. The intervals above all have the same length on them, with the midpoints actually midway. More generally, a point midway between 2 points corresponds to the generalized f-mean, with f the corresponding function log x or slog x. In the case of log x, this mean of two numbers does not depend on the base of the logarithm, just like in the case of log x, but unlike in the case of log x.